Good day, students. Welcome to mathcodeserve.com. In this clip, we're going to be focusing on how to find the domain and range of functions graphically. All right, so the instructions are for the given graph, find the following. So to find the span of the graph, basically the domain and the range. You should describe the behavior, intervals where it's increasing, decreasing, or constant. The extrema value, where do you have the relative and absolute min and max, and at what are the values. We also to determine the symmetry of the graph, if it is odd, even, or neither. Okay. All right. So we're going to start with this graph that we have right here. Let's start by taking a look at the span, the domain, and the range. So let's start with the domain. Now, what is the domain graphically? Well, the domain of the graph of a function is what you get when you project the graph onto the x-axis. All right, so what you do is imagine that you have a flashlight above and beneath the function. So what you're going to do is you're going to project the portion of the graph above the x-axis onto the x-axis, and the portion of the graph beneath the x-axis onto the x-axis also. So when you project the graph onto the x-axis, when I mean projection, imagine flashing a flashlight onto the graph and asking yourself, what kind of shadow will the graph cast on the x-axis? Okay, so let's go ahead and sketch what that would look like for the x-axis. Okay, so if we project the graph onto the x-axis, what you end up with is something like this. Okay, you have that line, the entire x-axis. So the domain of the graph spans the entire x-axis. So what we're doing is basically projecting. You see this tip right here gets projected downwards. That tip gets projected downwards. Oops. Let's do that again. That tip right there gets projected downwards to there, and then all this portion above the x-axis, they get the shadows are casted right there, and this portion beneath the x-axis has a shadow cast right here, and this portion above gets a shadow cast right here. So you have this entire line as the projection of the graph onto the x-axis, and that is your domain. Okay, so there are different ways you can write this. You can write it as R, or you can say the set of real numbers, set of all reals, or you can write it in interval notation from negative infinity all the way to infinity. This is the horizontal span of the graph. Now, what is our vertical span? The vertical span of the graph. Now, what we're going to do in that case is we're going to take our flashlight and we're going to project the graph onto the y-axis. So the portion to the left, just project it on the y-axis. The portion to the right, just project it on the y-axis. So if you flash a flashlight onto this graph, what kind of shadow will be cast on the y-axis? That's the projection of the graph. Or think about it this way: how low does the graph go, and how high does the graph go? That's basically what your range is, the vertical span of the graph. Okay, so if we carry out our projection, this is the lowest point, because if you look at the end behavior of these arrows, they indicate that they're heading upwards. So this lowest point will be projected right here. We have a high point here, but this arrow is going to go up forever. So eventually we're going to have an arrow that's going to be somewhere here, okay, pointing upwards. So what will our vertical projection of the graph look like? The projection on the y-axis is going to be from this low point heading all the way to infinity. Okay, from now, let's see, what is this? 2, 4, 6, from -4 all the way to infinity will be the vertical span of our graph. Remember, this arrow is pointing up because we have this end behavior heading upwards, and this end behavior heading upwards too, because eventually they will exceed this maximum, relative maximum value of positive 10. Okay, so let's go ahead and write down what our range is in this scenario. Our range is going to be you're going to go from -4. So you have a closed circle there, so -4 is included, and you increase all the way to infinity, parenthesis. Or if you want to use inequality notation, you can simply say y is greater than or equal to -4. That will be the vertical span of your graph. Okay, now let's talk about the behavior of the graph. On what intervals is the graph increasing and decreasing? Okay, so behavior. Now let's see. If we're always going to go from left to right, okay, when we're considering the behavior. Always go from left to right, and if you're heading down from left to right, you're decreasing, and if you're heading up from left to right, you're increasing, okay? So from negative infinity, remember we have negative infinity here, and we have positive infinity at the right end. So from negative infinity, going from left to right, the function is descending on that interval, and then it goes up and then descends again, descend, goes up and then descends again, and then goes up. All right, so those are the intervals where the graph is decreasing. So let's write that down. So it's decreasing. We're going to use interval notation, okay? So it's decreasing from negative infinity to, we're only looking at the x-axis projection, okay? So from negative infinity to -8, union, you jump to where? From -2 all the way to 0, union from 2 all the way to what? To 5. And those are the only intervals that the graph is decreasing on. Now, how about increasing? So where does it go up from left to right? From -8, it goes up, 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 up to this relative max, dips down, and then here it goes up again, up, 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 all the way to 10, drops again, and then here it just takes up, 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 up forever. All right, so that's the interval where the function is increasing on. Okay, so let's write that down. Increasing. Where is it increasing? It's increasing from -8 to -2, and then from 0 to 2, union, and then finally from +5 to infinity. So that's the interval where the graph is decreasing. Okay, now let's talk about the extrema end value. Okay, so let's write that down, extrema value. For this one, we're going to state what the extrema is and where it occurs at. Okay, now when we think about local and local max and min, they're also known as the relative max and min. We're looking at the peaks and the valleys. Okay, so all the peaks are the local maximums, and all the valleys are your local minimum. All right, so let's go ahead and start with our local maximum. Okay, so for our local maximum, we have two of them. Okay, so this is the first one right here. This is a local maximum. Any peak on the graph is a local maximum. So this is one of them, Lmax1, this point right here. And then this point right here is our second local maximum. Okay, so let's go ahead and write it down. So our local, or you can call it relative. Okay, local or relative max. We have two of them. The first one is you have a local max at x equals -2, the value of +6. And then the second local max is at x equals +2 with a value of what? Value of 10. All right. Now we have our local maxima. Now, do we have an absolute maximum? Is there a point here that's the highest in the entire domain? These two are local, but take a look at the end behavior. This indicates that this function increases without bounds, and this function increases without bounds in the left and the right ends. So does this indicate that these values will be exceeded? It certainly does. Is it going to stop increasing? The answer is no. Since it increases without bound, then there isn't a maximum value for this function. It increases forever. Okay, so the global, or let's say the absolute, also known as the global max, in this case, you have none because of the end behavior indicates that you're going to be increasing forever. Okay, now let's consider our local or relative minima and the absolute or global minimum. So we're looking at the valleys, okay, the low points on this graph. So here, at this point right here, we have a local min as the first one. And then here we have a local min, second one. And here we have another local min. Okay, so we have three local minimas in this function. So let's go ahead and write it down. Our local, also known as relative, minima as follows. We have three of them. The first one is at x equals -8, a value of -4. Next, we have a local minimum at x equals 0, and the value of the relative minimum there is a value of 0. Last but not the least, we have a local minimum at x equals 5, and the value is the same as the other one, value of 0. Okay? Now, do we have an absolute or a global minimum in this graph right here? The answer is yes. Notice that at the end behaviors, they're increasing forever. Okay, so we can easily compare our local minimas and the lowest, the smallest or the lowest minimum out of all these three. Minima will be your absolute um, minimum. Okay, basically the lowest hanging fruit, if you want to look at it that way. You can clearly see that this is the lowest value. The lowest value here is -4 compared to these two, which have the same value of 0. So since this is the lowest of the lows, that is your absolute minimum because the function goes up to infinity in both directions. So we have an absolute minimum at x equals -8, and the value is value of -4. Okay. All right. So just a key takeaway here is that your absolute is always one of your local, but not all your locals are going to be an absolute. Okay. Sometimes you can have locals and none of them are absolute, but whenever you have an absolute, it is also automatically a local or relative mean or maximum. Okay, so the last thing we're going to talk about is the symmetry of the graph, okay? Is this graph odd, even, or neither? So when we're looking for the symmetry, if we want to determine the symmetry of the graph graphically, well, all we have to do is split the graph down the center, okay? All right, so let's test if it's even first, okay? If it's even, then it will be symmetric about the y-axis. So what does that mean? It means that if we reflect the right side of the graph, across the y-axis, we'll get an identical image on the left side. So if you have a paper, one thing you can do is simply fold the paper down the center and fold it. And if they are two identical pieces, then it's even. Okay, but I'm going to use a computer to show you how it looks. So I'm going to split the graph down the center. Now what I'm going to do is I'm going to use the computer program to flip this piece okay, across the y-axis. So I have it flipped. And the question we're going to ask ourselves is, are these two pieces identical? The answer is no. So since they are not identical, that means that the reflection about the y-axis does not yield an identical curve. So this graph is not symmetric about the y-axis, hence it is not even. Okay, so say it different. So since the halves are different, the graph is not even. Okay, it's not even. All right, how about um, odd symmetry? How can we test to see if this graph is odd or not? Okay, so to test to see if the graph is odd or not, what we're going to basically do is take half of the graph and rotate it 180 degrees and ask yourself, do you get an identical image after rotating half of the graph by 180 degrees? Okay, that's the question. So when we're talking about odd, that basically involves a rotational symmetry, a symmetry about the origin. Okay, so let me show you what I'm talking about. Let's split it down the center. See if you can visualize this. If I rotate this graph 180 degrees, do I get this identical graph? You will not. Okay, so let me go ahead and do it. So 180 degrees right there. Now, are they the same? The answer is no. Okay, so this graph is not symmetric about the origin. So since the two halves are different, this function is not odd. Okay, so let's write that down. Since the halves are different, the function is not odd. Okay, so it's neither odd nor even, so the symmetry basically is going to be neither. Okay, so it's neither odd nor even in this case. Okay, now in the next set of problems, we are going to be learning how to use our graphing calculator to graph functions and then to basically analyze the functions by answering these questions with the resulting graph that we have. Part D has some algebraic components to it. After we determine the symmetry of the graph, we're to verify algebraically that our answer is in fact correct. Okay, so let's take a look at the first example, question number 2. Let's say we have the function f of x equals 3x squared minus 2. So we're to graph this with a graphing calculator. All right, I'm going to be using the TI-83 here. So press Y, enter the function 3x squared minus 2. Enter. Okay, and then to graph, you just press, graph is right here, just press the graph button, and there you have the function. Okay, now let's go ahead and answer the questions. What is the domain of this graph? So it's going to do it. So the span domain. Domain is the width of the graph. Now, if you think about what the graph looks like, you have something like this, and it's a, let's call it back up. It's a parabola that's been shifted 3 units down. So your vertex is going to be 3 units down, 1, 2, 3, and it's something that just goes up like that. Okay. So what's the horizontal span? If you project this graph onto your x-axis, what you're going to have is the entire x-axis. Okay. Because this arrow has a slight tilt, that means that the width of this graph is unconstrained. It's going to keep going wider and wider forever. Okay, so this tip right here gets projected downwards, this tip gets projected downwards, and you have the entire interval going from negative infinity to infinity. So the domain here is, you can write it like this, or you can say all reals, or you can say from negative infinity to infinity as your horizontal span. How about your range? What's the range? In this graph, it does have a minimum value right there, okay? So what's the minimum value? Actually, this graph has been shifted 2 units down. I said it incorrectly. If you want to find a minimum value, there's a function here that can help you calculate that. Press second function calculate. You see that minimum? Scroll down to 3, left bound. Scroll to the left of the point. Press enter. Right bound, you scroll to the right of the point. Press enter. Guess, enter. Minimum, well, this calculator has an ancient software. It's -2, okay, and it's at x equals 0. So that's where your minimum is. So the graph goes from, let me adjust this a little bit. It's supposed to be 2 units downwards. So the graph basically goes from -2 all the way to infinity. Okay, so if we project the graph onto the x-axis, what we'll have is something like this. You're going to go from the minimum and you go up forever. That's what your range is going to be. Okay, so let's write that down. Our range, the horizontal span of the vertical span of the graph, you're going to go as low as -2. So we're going from -2 included all the way up to infinity. Okay, or you can say y is greater than or equal to -2 as your range. Okay, let's talk about behavior. All right, I took a snapshot of the graph, so we can just work with that. Okay, so for the behavior, we see that the graph descends all the way down to what? All the way down to 0. And after that, it starts to ascend all the way to infinity. Okay, so let's talk about behavior. The graph is decreasing from negative infinity all the way to 0. Okay, and then it's increasing from 0 to infinity. All right, let's go ahead and discuss the extrema of the function. So let's write that down, the extrema and value, okay? We're going to be starting with the maxima, okay? Relative and absolute. Let's start with the relative. Local or relative maxima. Now in this graph, if you look at the end behavior, it goes up forever. So at the endpoints, we don't have a maximum. And if you take a look at the interior points, do you have any peaks in this graph? The answer is no, you only have a valley, which is right here. Okay, so what does that tell us? Concerning local or relative maxima, we have none. All right, how about absolute? Also known as the global maximum. Do we have any? We don't have any, okay, because we do not have any absolutely highest point at any point in the interval of this function. So we have none also. Now let's talk about the minima. Do we have any local or relative minima in this graph? So in that case, we're looking for valleys, okay, or low points. So in this graph, we have a valley right here, a low point. That is the only local minimum that we have. All right, so our local minimum, we have a local minimum at x equals 0. and the value is y equals -2, as indicated here. Okay, if you take a look at this number, this is basically 0. All right, it's just a silly programming way of rendering 0. Anyway, so that's your relative min. Now, do we have an absolute or global min? The answer is yes, because if you look at the end behavior, the left end behavior is infinity, right end behavior is infinity, so they will go up forever. So we know for a certainty that this is the lowest point, okay, forever in this graph. So the absolute minimum happens to be the only local minimum that we have also. So it's at x equals 0, and the value is y equals -2. All right, now let's take a look at the symmetry of the graph. Is it odd or even? So if you take the graph and you split it down the center, what do you notice? You have a mirror image. The right side is a mirror image of the left side. Okay, so symmetry about the y-axis means that the graph is even. Okay, so symmetry, the graph, the function is even. Why? Since it is symmetric about the y-axis. Okay. Now let's verify this claim algebraically. Okay, so verification. In order to determine if a function is even or symmetric about the y-axis algebraically, we have to verify if we have to show that f of -x is equal to f of x. So if you take all the x's in the function and replace with -x, and you simplify, you end up with exactly the same function that you started with. If that case holds, then you know for a certainty that your function is even. Okay, so let's go ahead and carry out the test. The function is 3x squared minus 2. What is f of -x? That's 3 times -x squared minus 2. Let's simplify that. -x squared, since the negative is in the parentheses, is squared, so it's going to become plus. So we have 3x squared minus 2, and this is the same thing as f of x. So our initial conclusion is correct. The function is an even function. Thank you so much for taking the time to watch this presentation. If this tutorial was helpful in your study of functions, behavior, symmetry, and extrema, do give us a thumbs up. Your positive feedback is very valuable to us. Any questions or comments, just include it in the comment section below, and we will be more than glad to support you. Don't forget to subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on mathcodeserve.com. Thanks again for watching and have a wonderful day. Goodbye.